Hey, hello, my name is Till. I'm from Germany, right now in Hong Kong. I studied maths and computer science in Oxford, but I'm really interested about everything in the world, from science, technology to history and society, and I'm always happy to learn more, and I'm here to learn together with you.
Hi guys, I'm Krystal. I'm a second year chemistry student at Oxford, and today I'm having a discussion with Till about academic disciplines, like in different subjects. So whatever we're interested about, you'll find out the topics.
Let's go.
Okay, so Till, are you interested in how we see colors in fireworks or flame test?
Colors, fireworks, and what? Flame? What?
Flame test?
Flame test.
Have you heard of that?
Sounds like something from long ago in chemistry lesson.
Yeah, we
okay,
do that.
I love colors. I love colors. Colors are beautiful. So
yeah. So do you know that actually the colors we see from fireworks actually works in the same way as the colors we see in flame test?
So that's like stuff burning and then releasing some radiation of a certain frequency, right?
Yeah.
Okay, yeah, I'm not an expert in colors, but I know colors are electromagnetic radiation with a certain frequency. That's what I know, but I'm a bit hazy on the details of how certain chemicals, when they're burned, like what exactly happens.
Oh, okay. So actually, when we see colors, so we have some metal ions in our view. So for example, we have like strontium that makes us see red color.
I remember that, yes.
Yeah, and then we have sodium that we see golden yellow. Mm-hmm. So that's the color that we see in fireworks, and when it works, like, it's the same concept as the flame test. So it's all about electrons excitation. Have you heard of that?
Yes, I've heard of it. It's like, I know it's not the real model, but this whole like electron shells. I know it's more like quantum physics and like electron clouds and that stuff, but I know that somehow there is something like, there's some quantum electrodynamic stuff going on of like electrons getting energy at certain like energy levels, and then they're wanted to get rid of their energy, and then somehow they release radiation by going to a different level or something. I don't know. Can you fill in the gaps?
Okay, so we know that colors are electromagnetic radiations,
yes.
Right? So with visible light, which is the colors that we see, is about 300 nanometers to 700 nanometers for the wavelength. Mm-hmm. Yep. And then so the higher the wavelength, then it would be a lower energy radiation. So that would be the red color that we see on the spectrum. Mm-hmm. And then for the high energy, it will be like violet, purple, like the darker side that we see from the spectrum.
Right.
So in chemistry, we explain the colors by using energy levels, as what you said. So it's basically that we have discrete energy levels, in atomic level. Mm-hmm. So inside the atoms, we have like discrete energy levels. They can only take certain values, but not continuous values.
Right.
Yeah. So what do you think will happen if we supply energy to an electron? Do you think it would jump up in energy or jump down in energy?
Well, I mean, I'm not sure if this is a trick question, but I mean, of course, like I guess if it's the right amount of energy, it will go to other level.
Yeah.
But what happens if it's not? If it's like halfway there, does it just pass through? It just totally ignores it?
Yeah. We can't have energy levels in between the energy.
Yeah, but if it's the
so
right level, then like,
then
yay!
you can jump up to the energy level that you want. Yeah, so that's what we call excitation of electrons. We excite an electron from a lower energy level to a higher energy level, but eventually that electron has to decay back down. It has to come back down. So when it comes back down, we know that energy is conserved. So that energy has to go somewhere. So where do you think it's gone to?
Light.
Yeah, colors. That's the colors that we see.
Yeah, okay.
Yeah. So depending on what the energy gap is, so depending on the energy gaps in different metal ions, we will see different colors. So the energy gap, if it's closer, is smaller energy, then we see like colors like red and yellow, like in strontium and sodium. But if we want to see like green colors, we then have like copper, for example, that's high in energy.
Yeah. Okay, I have a question there, because I've always wondered this for a long time, but the answer seems to be very complicated, and I never really studied this. So, like, I know somehow that these different elements have different specific energy levels that they like, right? And then, therefore, sometimes you can see in a flame test, this color means this element is present, right? Yeah. Or you can have like a certain peak in a spectrum or something. But, like, why? Like, if you just, elements, you just have neutrons and protons and a bunch of electrons. Like how do we know? How can we predict what are the energy levels or what are the colors? Or we just have to find it out? Is there any kind of model to explain it? Does it have to do with the periodic table or just with the number of protons and neutrons? Or like how do we know what is a good energy level for an element?
So it all depends on the number of protons and electrons that we have.
Okay.
And there's something called the Schrödinger equations, which is actually fascinating. Like no one ever understands it, no one ever knows what it is, and no one knows how it comes out.
Oh, but I know one thing, because he's German and I know how to pronounce it. I have no idea how to interpret it. It's called Schrödinger.
What?
Schrödinger.
Schrödinger. Okay, I give up. Okay, never mind.
But that's a limit. Like I know how to say it, but I don't know really what it means.
So it's basically a differential equation. And it's very complicated, but then when you solve it, depending on the number of protons and the electrons we have, because the more protons you get more attractions between the positive charge and negative charge, but then you also get repulsions in between the electrons in the same atom.
Right.
So depending on those, it will come out as different values that we can take. Yeah.
So solving the Schrödinger equation actually tells us kind of what are the colors of different elements.
It kind of tells you like what the energy gaps are, and then from the energy gaps, then you can work out the colors.
So this is not something. So basically, this is not something purely empirical that you just find out and test, and you like. I guess this is how they found it out, but like you can kind of calculate in a mathematical way for the elements.
But the fascinating thing is no one ever knows how he came up with the equation. No one can ever prove it.
Yeah, and he's not alive anymore.
Yeah, and there is actually another way that we can see colors. So the one that we talked about is called an emission spectrum, because the electron decays back down and emit the color, emit the energy that we see. There is actually something called the absorption spectrum. So when we absorb color, we can also see the rest of the colors. So that actually happens in transition metal complexes. So like transition...
Wait, transition metal complex. Explain all three things, please.
So transition metals, so they are like the metals they're d block elements. So with orbitals in the electrons, so orbitals are basically where the electrons are, the space that they can take. We have like s orbitals, p orbitals, d orbitals, f, g.
Yeah, I remember this from chemistry. I never understood it, but okay.
Yeah, so basically there are layers of orbitals inside an atom, and with transition metals, they all have d orbitals. And the d orbitals actually makes us see the colors in transition metal complexes. So what's a transition metal complexes? It's actually a central metal ion.
Okay.
And then we have got like different sort of negatively charged ions or molecules around it, forming like an octahedral structure, for example, that you can imagine.
Okay.
Yeah. And then we will see color by actually the d orbitals splitting in energies. But with the d orbitals, do you know whether they are at the same energy or different energies at the beginning in the metal ion?
In the metal ion, if they are, what are different? What?
So inside a metal ion, we have like s orbitals, p orbitals, d orbitals.
Okay.
And all of those orbitals actually had the same energy at the start. So all the d orbitals have the same energy.
Okay, yeah, okay.
And all the p orbitals.
I guess that's what an orbital means, right?
Yeah. So
Okay.
they are degenerate. That's what we call in
Okay.
chemistry. Yeah. They all have the same energy levels, and then they actually split in the transition metal complexes. In the complex, we have the metal ion in the middle with all the d orbitals surrounding it. But then, like, we have some ligands that comes
What
into
is that?
it. Ligands are actually just negatively charged ions or some molecules with a lone pair. So they can bond to a positively charged metal. You can imagine, right? Positive charge and negative charge, and they
Makes
attract,
sense.
and then
Okay.
they kind of like come together. Yeah, and then in that, when the ligands come in, because they're negatively charged, what do you think will happen between the d orbitals that has the electrons inside in the metal ion and in the lone pair, or like the negative charge in the ligands? Do you think they will attract or repel? Is that too hard?
No, I'm trying to visualize it, and I'm still. No, I have no idea. Okay, you tell me.
Okay, so should I? Okay. We have a metal ion here.
Okay.
And then we have like all the orbitals around it.
Yes.
And then these orbitals, because they have d orbitals especially, they have electrons.
Yes.
So they have electron density.
Yes.
And then we have all the other ligands, like water molecules, for example,
Okay.
with lone pair of electrons in oxygen coming in towards the central metal ion.
Okay.
So they are attracted to the central metal ion because it's positively charged, but they will repel with the d orbital electrons around the metal ions.
Yeah.
Yeah. So depending on the direction they come in, the d orbitals, which were in the same energy levels, they will now split.
Okay.
They now split into different energies.
Okay, I kind of get that. Although I'm still a bit confused how I feel like if you think of it from the outside, that like you have the ion and you have the electron orbitals somewhere around it, but how can you be attracted to the ion with all the electrons around it? Wouldn't it like somehow mathematically in the end cancel out, or in the end you would have a stronger repulsion because you're closer to the electrons? Like how can you actually be attracted to the ion?
So that's when we use a model, because the crystal field theory, we model the central metal ion is positively charged because it's an ion, so it has lots of electrons, so overall it's positively charged. And then we treat all the ligands that we call them like negative point charges. So this is essentially it's just a negative charge. And then so we can imagine them attracting together because it's positive, it's negative.
Of course, but we still have those electrons
we
around.
still have those electrons, but they're still attracted because the overall charge of the metal ion is positive.
Overall yes, but at some point you kind of get very close to the electrons, right?
Yeah, and then they repel.
Right, yeah.
At that point, so they're still attracted, but they kind of experience some kind of repulsion.
Yeah.
And that repulsion will actually cause an energy splitting in the d orbitals in the metal ion.
Got it. Okay.
Yeah, and then depending on the energy gap, we will see different colors. So have you ever seen vanadium solution? Vanadium. I
have no idea what that is.
No. Okay, so it's just a solution that you see in a chemistry lab, and then if you have like vanadium 2+ and vanadium 3+, you see different colors. So depending on the oxidation state of the electron,
that makes sense.
Of the metal, and then we see different colors. But why?
Well, I would guess because if they have different oxidation stages, they have different behaviors of the electron splitting and the energy levels, right?
Yeah, exactly. So if we have a 3+ ion compared to a 2+ ion, 3+ ion is a higher charge. So we would imagine that it would draw the other negative charged molecules closer, right?
Right, yeah.
So if we draw them closer, we will experience more repulsion.
Yeah.
If we experience more repulsion, that means the energy gap splitting will be larger.
Yeah, right.
So if that is larger, then we would absorb a higher energy, so higher energy color. That energy comes from white light. So like the white light that we see, that consists of all the wavelengths, so red, yellow, whatever that you see, and then subtracting the energy that actually gets absorbed, then the remaining color would be what we see. And we actually call that the complementary color. So if we absorb purple, then we see yellow. So vanadium 3+ is yellow because of this, but vanadium 2+ is purple.
Right, yeah, cool. So it is kind of cool, and it's kind of neat how something as natural as color, when we like grow up, we think color is just something intrinsic, but you can all explain it with like electrons and energy levels. It is kind of cool, but I really wonder is how did researchers figure this out? It's not like you can have a microscope and observe electrons like repulsing ions and stuff like this. It's not like you can see it, right? So you have to either have a crazy imagination, or you have to find controlled experiments where you can actually isolate all these variables and figure out this is exactly what's happening. Or is it just some random theories that people say is probably true? Like how do people figure this out?
I think they actually thought about it because they had, so we talked about energy levels, right? Schrodinger's equation, they were able to like solve that different atoms or different metal ions, they have discrete energy levels. And then from there, they then made a hypothesis. So the crystal field theory is that all the ligands are just negative point charges. So they just basically use what I said, like as a model, and to say that, the d orbitals will now split. And then when they do a measurement, they realize that energy splitting, the wavelength actually comes out to be the same as what we predicted.
Right, okay. So someone has some crazy idea, and then we predict something on the idea, then you measure it, it's like, then that model is probably true.
I wish I'm that
Yeah,
smart.
that's crazy. No, but I really like that as well. It's like, when I was first interested, I was like a teenager, and I was first interested in things like nuclear physics, was mostly just because all these terms sounded so cool and like science fiction and stuff. I was just a teenager and we're not learning this in school. And then I was reading one book, and then I realized actually you can totally imagine things. You can imagine electrons, you can imagine nucleus, you can imagine those interactions happening, even though it's just a model, but it's something like physical to imagine. And that actually helped me a lot, and that helped me actually be interested in it, because it's not like the attraction was not like, oh, this is very applicable for your everyday life, but it's not, no, like, this is a phenomenon we see, but actually we can zoom in all the way, imagining zooming in all the way, and imagining the mechanics of the things happening, and I find that really cool.
Yeah, exactly, very interesting.
That's chemistry, yeah.